presses, which are very efficient. So basically, this is the backbone of any power system. Like in the generation plants, we have a thermal power plant, hydropower plant, nuclear power plant to generate a very high amount of voltage, which can be further stepped up by the transformers on the grid side, on the power plant side, which will be transferred through the AC transmission systems. We have the power transformers to step up the voltage, and we have a surge arresters, lightning arrestor to rectify or to eliminate the surges due to lightning or any switching surges, which can generate transients voltage, which are very dangerous. We have a switch gears to locate the fault and rectify it, like we have a circuit breakers, air brake circuit breakers. In the distribution side, we have a substations. There we have a feeders to supply the power to the consumers. So we have a review of some researches in the control and power engineering. This is the basic structure of the power system. We have a generation. Today's we are using a distributive energy generators like solar and wind power plants to generate the powers. But in distributed means we can generate powers to consumer side as well as to fulfill our demand, as opposed to the grid side power. When there is an outage in the grid side, then we can utilize our appliances to our own generation, like solar photovoltaics panels. Here we have a generation through we can transfer power to the grid. And we have a generation. So in case we have a surplus amount of power, we can deliver it to the grid. And when we need any power, so we can take it from the grid. So that's why we like. So the main thing we need to consider, like the grid stability and power quality, are the main concern, because the power we deliver to the grid or we take should be good, means being contains less amount of harmonics, as IEEE standard, like below 5%. And the grid stability is very important. While in case of outages like SAC, so that time we should deliver reactive power to the grid. There should be a continuous power supply. Renewables integration. Yes, if we want to operate our grid in an isolated mode, suppose there is any outages, then we can fulfill our demands, electrical demands. If we have a very ample amount of energy, we can deliver the grid. So we can reduce our tariffs as well. FRT capability means if we want to deliver power to the grid without any interruption, so we should have very low voltage and high voltage right through capability, which can handle power and continuously deliver it to the grid whenever there is a sag and swell in the grid voltages. We have power electronics, which we using nowadays as advanced FACT technologies, and which contains a STATCOM based and SVC based sun compensation devices, and SSC static synchronous compensators in series compensation to deliver reactive power when there is any voltage dip and swell in the grid. SVTC technology, as we know that intercontinental power delivery needs a very huge distance, like under the water we need to deliver power, so which is not possible through the AC cables, because there is lots of losses are there, like there is a Ferranti effect and skin effect. These are some of losses, and there is a parasitic capacitance in case of AC if we are delivering long distances. So SVTC is a very best technology. Here we have a power converter which we use to convert DC to AC or AC to DC. In case of electric vehicles or SVTC technology, we use DC to AC converters or AC to DC converters. In my work, I use modular multi-level converter because of its advantage like modularity and scalability. So power switches like IGBTs and MOSFETs, power MOSFETs are used there. And the converter topologies, as I mentioned, that modular multi-level converters and like edge bridge converters, but modular multi-level converters are very efficient. SiC and GaN semiconductor technologies, which make the semiconductor capable of handling high amount of power and make them thermally stable. So SiC and GaN are the latest semiconductor-based technologies which are very efficient. This is a basically a modular merge level converter schematics as well as the circuit. So IGBTs are used because the main advantage of the modular merge level converter is that the devices we use has to handle a very less amount of voltage. So there are low voltage rating devices we can use as opposed to the line commutated converters or edge bridge converters, where we need to have high rating switching devices like high rating power MOSFETs. So IGBTs prove to be a very good competitor. So these are basically some of the power switches like BJTs, thyristor, MOSFETs. Basically, IGBT is the takes the good traits of BJT as well as MOSFET. Like in case of BJT, we have a low conduction losses, or if we operate in the main advantage of MOSFET, that we can operate it at very high frequency. So these are comprise the two good qualities of those MOSFET and BJTs. The main benefit of thyristor that the thyristor bulb can handle a high power rate, high amount of power. It comes with high power rating. The main problem is that it needs protection circuitry like snowball circuits and commutation circuitry that makes it very complex. But in medium and high power applications, somewhere we use thyristor. But after advent of highly efficient converters that make it possible to use IGBTs. So IGBTs needs a bypassing diodes to operate, make it a two-quadrant converter, two-quadrant switches. But thyristor itself operates in two quadrants, because as we know that we can apply positive and negative voltage to a thyristor. So there is no need of any anti-parallel diode. But in case of IGBT, we need a bypassing diode to make it operate in two quadrants. So basically, these are some applications in power system engineering, like the solar PV applications. We have a smart grid, and in electric vehicles as well, we have a lot of application. In case of drives, we need to deliver high quality power to the drive through DC-AC converter. We have battery bank, and where we need a AC to DC converter to receive power from the AC infrastructure, charging infrastructure, so efficiently convert it into DC to charge the battery. In case of smart grid, which is a very recent technology where we can operate our grid efficiently in a smart way. We can, in a digital way, like when there is a load for in traditional, we cannot forecast the loads. But in case of smart grid, we can we having a smart meters. We can real time read the consumption of the consumer, so we can accordingly bill them. So this is the main benefit of smart grid, as well as we can there is an interoperability of different elements like the solar, wind, or we have electric vehicles. We can charge them. So this makes the ecosystem very reliable. So this is basically the traits of the smart grid, like digitalization. We can we can receive a real-time data of the consumer activities. We have decentralization. We don't need any great dependency. We can generate by power itself to fulfill our daily needs. And obviously, it's a green technology. So as opposed to our conventional based sources like coal-based fossil fuels, which are very we are not economic and environment friendly. So this is the main benefit of distributed energy generations. These are some control engineering applications. Like in drone, we have a BLDC motors. In case of robotics like cobots, we have a small motors like BLDC switch reluctance motors to efficiently control their position. In case of electric vehicles, we need to control the speed of the motors with the help of DC to AC converters efficiently. Recently, we using sync RM motors and BLDC motors in the electric vehicles because they are very efficient, they are loss free, they are very economical, as well as the recent advances in the motor is yokeless axial flux motors, which are very efficient and compact. So this is also the part of the high-tech motors technology. In case of smart meters, we know that accordingly we are sending the details of the consumer activities to the substations to monitor the activity of the consumer. Simultaneously, we are billing them. We give the real-time data of their consumption of the devices. So these are main benefits of these smart meters. These are some of the challenges like harmonics mitigation, because as we know that we are using a power electronic converters devices, but simultaneously they are generating a harmonics in the load as well as source side. So the main difficulty is that these type of power electronic devices are very prone to harmonics. Dependency of rare earth metals, because we use motors, we use rare earth magnets like neodymium magnets or samarium magnets, which are rare earth based magnets. So research is on the electromagnets, which are not rare earth based magnets. So we don't need to take the earth to take all the magnets. So that's not a good. Batteries and reliability, as we know, the lithium-ion batteries are very temperature sensitive. So we have a BMS. So good algorithm like metahistoric based algorithms take care of the battery's activities like their SOH, state of health, which continuously measures the battery's activity like their temperature, charge balancing. But somehow it is very sensitive materials. So like in case of lithium-ion batteries, which are very temperature sensitive, as I said. So some way it is very needed that we should take care of them. So there's a load forecasting. In smart meters, we have solved this thing, but it is also day by day. Suddenly the load changes. In summer times, the people just abruptly change their load, means appliances, they are opening the fan and etc. So it is very difficult to always track all those changes in the load. So power quality is also the part of this. So in the grid side, we have to deliver the power, which should be according to the IEEE, as per IEEE standard. We have to compensate some of the reactive power to maintain the grid voltage. So there we use some shunt compensation devices like STATCOM series compensators. In cybersecurity as well, we are in autonomous vehicles, or in case of electric vehicles, we use telematics-based technology. So it is also prone to the cyber threat. We can so it is the main concern. And last one is a highly nonlinear systems. In control system engineering, like we use a model predictive control to predict the system output, but that's optimization based on the online. So it is online, but we need to solve those optimization techniques, but it's very time consuming. But the real type systems are very non-linear, so we need to design such controllers which is very efficient, which does not take as much space. Solve those plant models to generate the output according to the means situation. Like we have a vehicle, so we can forecast the any further means is there any accident, so we can real time we can change the direction of the vehicle. So like it's a basic example. So the real time situations are basically highly nonlinear systems. So in case of meta-heuristic optimization, we what we use that we optimize we make the model and solve those models. Means like example, we PSO models. So PSO based algorithms or genetic build algorithms we use to solve those highly nonlinear systems. So this is also part of the research. So these are some of the references related to my work. Basically, my work on the field of BMS and multi-level inverter. So thank you very much for your kind.